Okay, how's everyone doing today?
Really awesome, sir.
Jessica, how are you feeling?
I'm great.
All right, awesome. All right, so, ladies and gentlemen, today we're going to pause from the regular syllabus and we're going to address this question here. What is the difference between conservative work and non-conservative work? So, recall yesterday we talked about how if you do work on an object, the amount of work that's totally done on an object is equal to the change in the kinetic energy. So basically, you could write an equation that the total work done always equals the change in kinetic energy of the object. Now, of course, the change in the kinetic energy of the object could be rewritten. So you could say that the total work done, which would be the work done by all the forces acting on the object, is equal to the final kinetic energy minus the initial kinetic energy. And then we could just algebraically rearrange this by adding the kinetic energy over to the other side, and you end up with the initial kinetic energy of an object plus the total work done equals the final kinetic energy. So recall, kinetic energy is the energy of motion. So if an object is moving along and has yay much initial kinetic energy, and then you do more work on it, it's going to end up having an even greater amount of kinetic energy in the end. So it could be as simple as if an object had 50 joules of kinetic energy, and then you did another 10 joules of work on it, the new amount of kinetic energy it's going to have is 60 joules. Now we know that sometimes work can be negative. So if the object was moving along and had 50 joules of kinetic energy, but the total amount of work done was negative 10 joules, well, that means the force was going in the opposite direction of the displacement. It's slowing the object down, and the total kinetic energy now would be 40 joules. So this simplistic formula here, showing the hidden relationship between the initial kinetic energy and the final kinetic energy, it's sometimes called the work energy formula. Whoa, it's too big. Now you might recall that the formula for kinetic energy is 1/2 mv squared. So if you want to calculate the initial kinetic energy, if you know the mass of the object and you know the initial velocity, the initial kinetic energy can easily be calculated by 1/2 times the mass times the initial velocity squared. So 1/2 times the mass times the initial velocity squared, that'll give you the initial kinetic energy. And then if you add to that the total amount of work done, remember the total amount of work done is the work done by all the forces acting on that particular object. That's going to equal the object's final kinetic energy. And the final kinetic energy can also be calculated using that formula. 1/2 times the mass of the object times the final velocity squared. So this is another look of the work energy formula, but the kinetic energies are expanded out into 1/2 mv squares. And you could use this formula to solve for like final velocities sometimes. So what I want to do is go back and look at this problem we did. And let's say that the object starts from the bottom of the ramp, and let's say its initial velocity at the bottom was 0 meters per second. So it starts from rest. And let's say after it goes to the top of the ramp, when it gets to the very top up here, let's say we're trying to calculate the final velocity. Now we can do this two ways. One, we can go old school and use law number 2 from a man named Newton, along with the kinematic motion formulas. Or we can go new school and use our handy dandy work energy formula.
New school.
I want to show you guys both ways because it's good review to go over the older way, and then of course I want to show you how our new handy dandy formula works. So let's first try to solve for that final velocity, the velocity at the top, using our older formulas. Now, the first thing you realize is this object over here has a weight force. And I could draw that weight force like this. And we know that weight force, Fg equals m times g. So if the mass is 4 kilograms, F sub g is going to equal 4 kilograms times 10 meters per second squared. And you're absolutely right. It's going to be 40 newtons. So that's the whole Fg force, 40 newtons. But that weight force can be broken down into parts. And we were told that this angle right in here, was 37 degrees. So if you break that weight force down into parts, you could say, hey man, some of that weight force is pulling the object in this way. Some of the weight force is pulling the object down the ramp that way. The part that squeezes it in right into the ramp, that's referred to as Fg perpendicular. And the part that's squeezing it and pulling it down the ramp, that's referred to as Fg parallel. The diagram's a little bit cramped, so maybe I'll just re-sketch it out. So you have, and at the bottom right over here, here's Fg. And then Fg is broken down into parts. Fg perpendicular, and then part of Fg is pulling it this way. Fg parallel. And you might recall the formulas for calculating those. Fg parallel is equal to the whole weight force times the sine of the angle of inclination. So in this case, it's going to be 40 newtons times the sine of 37 degrees. And we might have calculated that in the past. Does anyone have that? Fg parallel?
I think we did that right.
24.
24 newtons?
Yeah. Does that, you want it rounded or?
Yeah, no, round's fine. And then Fg perpendicular is equal to the whole weight force, Fg, times cosine of theta. So that's going to equal 40 newtons times cosine of 37 degrees. So what does that turn out to be? 32 newtons. So Fg perpendicular right here is 24 newtons. And Fg parallel over here is, let me get this out of the way, is 32 newtons. But,
I think it's the other way around.
is it the other way around?
No, it's the other. Yeah, it's the other.
Yeah, it
Because you
is.
wrote parallel 4.4.
Oh, you're right, you're right. Thank you. So FG perpendicular is the 32 newtons, and FG parallel is the 24 newtons. And we still have that applied force pushing the object up this way. And what was that applied force? 60 newtons. And there's one more force acting on that sucker.
FN.
Fn, the normal force. The platform below it is pushing up on it, not allowing it to fall through there. And on an incline, what is the normal force equal to? FG perpendicular. So therefore it equals 32 newtons. So this FG force, I could kind of like cross out because it's being replaced by FG perpendicular and FG parallel. And remember, our whole goal is to figure out that velocity at the top. And now that we have all the forces shown there, it's going to be really easy to figure out the overall net force. If I want to know the overall net force, check this out. I see that I'm pushing it this way with 60 newtons, and FG parallel is holding it back there with 24 newtons. Now what about FG perpendicular and the normal force? What's going to be their deal over here?
Cancels out.
Yeah, they cancel each other out. So they're not going to be part of the net force. So the bottom line is F net is just going to turn out to be equal to the applied force pushing it up the ramp minus FG parallel. So in this case, F net is going to equal FA, 60 newtons, minus FG parallel, 24 newtons. So what's going to be the overall resulting force acting on that box? The overall net force?
36 newtons.
36 newtons. And law number 2 from a man named Newton says that if you know the overall net force and the mass, you can calculate the acceleration. So we know the overall net force is 36 newtons. And the overall mass was 4 kilograms. So what's going to be the deal with that box's acceleration up the ramp? So its speed is going to go 0 meters per second, then 9 meters per second, then 18 meters per second as it goes up the ramp. It's going to be accelerating 9 meters per second squared. So if we know the acceleration, and we know the initial velocity way down at the bottom of the ramp was 0 meters per second, and we know the distance up the ramp is 5 meters, what does that shout out in terms of what to go for, Janice? Good old no time formula. We know the initial velocity is 0. We're looking for the final velocity. We have the distance up the ramp. And now we have the acceleration. So that shouts out VF squared equals VI squared plus 2 times a times x, and therefore the final velocity squared is going to equal 0 meters per second squared plus 2 times, what was that, 9 meters per second squared times 5 meters, and the final velocity equals the square root of 90. And what's the square root of 90? That's going to be 3 times the square root of 10. Help me out there, someone crunch it out. Yoo-hoo! We figured out that velocity up at the top using old school physics. Second law of motion and kinematics equation. Now, let's go use our new work energy formula, yes? The new work energy formula basically says that the initial kinetic energy plus the total amount of work done is going to be equal to the final kinetic energy. And if we want, we can expand out those kinetic energy formulas. So the initial kinetic energy is 1/2 times the mass times the initial velocity squared plus the total amount of work done equals the final kinetic energy, which again I can expand out into 1/2 times m times vf squared. But what was the initial velocity at the bottom of the ramp? 0. So what's going to happen to that whole first term, the whole initial kinetic energy? It's out of there. Hasta la vista. Yes? And from lesson number 1, we calculated the total amount of work that was done pushing that ramp up. Do you guys have that in your notes?
180 joules.
How much?
180 joules.
180 joules? So we calculated that in a formal lesson. That's going to be 180 joules. And that's going to equal 1/2 times the mass of the object, which is 4 kilograms, times the final velocity squared. So if we solve this for the final velocity, once again, we're going to get the square root of 90, which is roughly 9.5. Woohoo! Chipperoo! I told you it would work. Now this way seems so much easier, but remember, we did a lot of work on it the other day when we calculated the total work. You know, recall when we calculated that total work, the total work was equal to the work done by the applied force plus the work done by the normal force plus the work done by the force due to gravity. And what was the work done by the applied force?
300 joules.
300 joules? And what was the work done by the normal force?
0.
0 joules. And what was the work done by the force due to gravity?
-120 joules.
And if you crunch that out, then we get positive 180 joules. And that's where we got this value right here. So we have our new handy dandy work energy formula. But here's what we're going to do next. You see this total work? We're going to break that work down into 2 categories. The non-conservative work and the conservative work. And in the future, the conservative work is going to be calculated or I should say replaced with potential energies. So at first you might be like, why are we doing all this? In the end, it's going to make our life easier because some of the work that's conservative, can be calculated much easily by using potential energy formulas. So this is where we're going. Initial kinetic energy plus the total work done equals the final kinetic energy. But this total work is going to be broken into two subcategories. Work done by conservative forces and work done by non-conservative forces. So it's going to have a new look. There's the initial kinetic energy, just like before. But now we're going to add the work done by conservative forces plus the work done by non-conservative forces. And when you add those two works together, that still gives you the total work. So therefore, what's still going to be on the right side of the equation?
Final kinetic energy.
The final amount of kinetic energy. You know, right here. That just got brought down. So we need to talk about what the heck is the difference between conservative work and non-conservative work. Here's the deal. If you have 2 points, point A and point B, if the work done by a force to go straight there is yay much, say 100 joules, and then instead of moving directly from A to B, you move the object through a different path. Maybe you slide the object over here, and then you slide the object up. Well, if the total work done to move it here and then to move it there is still 100 joules, then the work done by that force is said to be conservative. As a matter of fact, if you move the object along any path from here to there, if it's a conservative force doing conservative work, then guess how much work it would take to move it even down that curvy path from A to B? 100 joules. If it's conservative work, it does not depend on the path taken between the initial point and the final point. If it's non-conservative work, then the path that you take has a huge effect on how much non-conservative work is done. So basically, conservative work does not depend on the path taken from the starting point A to the ending point B. You're always going to get the same answer when you're calculating the conservative work. It does not depend on the path taken. And the non-conservative work does depend on the path taken from the initial starting point, A, to the final ending point, B. When we come back, we're going to look at examples of each of these. So stay tuned.